Okay, so here we go. We're talking about chords today. Specifically, we're going to talk about three properties. So these three properties really boil down to kind of two big conceptual ideas. So first, let's imagine we have some chord in this circle here, okay? So the first thing I could say is, well, that chord starts being in some direction, but let's just think about it for ease. Let's just rotate my circle until it's horizontal. Because whatever direction it started in, I could just roll the wheel over until that chord is horizontal. So let's just say that the chords we're looking at, we'll turn the circle so all the chords we're looking at are horizontal. That just being like a left, right eye person, that just helps me visualize symmetry and things like that. So I'm going to rotate our circle first and say we have a chord like that. Okay, so the two big ideas we've got are, the first one is the distance from the center determines that size of a chord. So in other words, I'll just take another color here. Let's say I'm in pink here. If I draw a chord here and then draw another chord, again, I could just rotate my chords so they're horizontal. If I draw another chord closer to the center, the closer to the center I get, the bigger my chord gets, until the biggest possible chord is the diameter. And then again, the further away from the center I get, the smaller chords get, smaller and smaller, until it would essentially be a tangent line where it just hits at a point and it would have a length 0 in terms of the point inside the circle. So the distance from the center really determines both how big the chord is from a maximum of the diameter length to a minimum of 0, and however far away you are sets that I am this size chord. And then also it goes the same for the arc. The arc starts at 180. The further away from the center you go, that gets smaller, maybe 160 degrees, maybe 90, maybe smaller and smaller until you're 10 degrees, 0 degrees. So that's kind of one big idea. The distance from the center sets a chord size and the arc size. The second big idea is, if I perpendicularly bisect, again, I turn my circle until my chord here is horizontal. If I cut this down the middle perfectly symmetrically in half, what I get is that the diameter is because this angle and this angle are the same, perpendicular, this side equal to this side, bisector. So the perpendicular bisector that cuts this chord perfectly in half at a 90-degree angle is the diameter, because it symmetrically cuts the circle into two congruent halves. Okay, so those are kind of the two big topics. The distance a chord is from the center sets its size. Further away from the center, the smaller that chord is. Closer to the center, the closer it is to the longest chord diameter. And then also, if I cut the circle in half, perpendicular to this chord, this perpendicular bisector is the diameter. Okay, and that one will kind of be this forward and backward, so we'll look at them separately. So we've got three properties, okay? Property number one we're talking about is two chords in a circle. Now this could either be the same circle or just two separate circles that are congruent. But two chords in the same circle are congruent if and only if their intercepted arcs are congruent. In other words, in this picture here, we have that if CD is the same as BA, if these two chords here are the same, well then we know, gosh, I keep saying chords and arcs, if those two arcs are the same, then we know the chords are the same. Or vice versa. If we start knowing these chords are the same, then that tells us that the arcs must be the same. Okay, those are interchangeable, if and only if, meaning if we have two congruent chords, they must have the same arc size. And vice versa. If we have the same arc size, then we have the same chord size. And again, that comes from up here. Once we've chosen a distance, we have that chord size set, the arc size set, and even if it's down, the same distance down here, we have that chord size and arc size set. Doesn't matter what direction you go in. Okay? So that's property number one. Chords are the same if and only if arcs are the same. All right, let's actually just do a problem on that first, okay? So before we go any further, here's a problem to find the measure of the red arc, okay? Well, we look at this, and this 34 says this line segment and this line segment are the same. Well, what that means is then this chord must be the same as this chord. Now, let's just call it X, okay? So they're both X long, or have a measure of x degrees. Okay, well, total in a circle, we know there's 360 degrees as we go around. So we could take 360, subtract 128, and get 232 degrees. So that tells us that from here at A, passing B and going to D, we have 232 degrees total. It's the rest of the circle other than the 128. And if we know these chords are the same, then the arcs are the same. So we just go ahead and divide that by 2, and we get each of these congruent arcs must be 116 degrees and 116 degrees. And that's one way in which we use that. So going back up here, I want to look at why this is true. Okay, we could prove it easily in either direction, and this is a proof that could maybe pop up on a test or quiz. But the big idea is, let's assume in the first case that we know the two arcs are congruent, and we want to see like why are the chords congruent. Okay, well, really common trick when dealing with circles is we draw in some extra radiuses. And the nice thing about that is we know that all the radiuses of a circle are congruent. Okay, and if the arcs are congruent, well, we know that the measure of an arc is defined by its central angle. So that would mean that these two central angles must be congruent if the measure of these arcs are congruent. And so look, by SAS, we have these two triangles are congruent. And if the triangles are congruent, then by CPCTC, we know that all their parts are congruent. So these two chords must be the same. Okay, so let's do a very similar proof the other way. Let's instead assume that the two chords are the same in this second proof. So we have two congruent chords. Let's draw in some radiuses. And look what we get. We get all the radiuses are the same. And so by SSS, these two triangles are the same. They have the same three sides in the two triangles. And if the two triangles are the same, then all of their parts are the same. So by CPCTC, we get that this angle matches this angle. And if those two angles are congruent, well then the measure of these arcs must be congruent, which means these two arcs must be the same. Okay, so it's a quick informal proof. All right, so let's look at the second property now. The second property is kind of three ways here. Essentially what this is saying is that if I have any circle and I cut a chord with a perpendicular bisector, okay, so I bisect a chord and it's perpendicular, then that has to be the diameter of this circle. It has to pass through the center. And in fact, what these two things essentially say is that if you have any two of three pieces of information, then you know the third. So if you know that it is a diameter and that is perpendicular to a chord, then you know it's the bisector. Or vice versa. If you have a perpendicular bisector, then you know it's a diameter. Or if you have a diameter that is a bisector, then you know it must be perpendicular. Okay, and that sounds a little funky, so let's go through one at a time. So the first one is, if one chord is a perpendicular bisector, right? So in this image shown, we have SQ is a perpendicular bisector of TR, then what that means is SQ must be diameter. So this must be a diameter. Okay, and it's kind of logical. If you spin a chord and you say, okay, here's the chord on top horizontal, so I'm going to draw a perpendicular line to that somewhere. And where am I going to draw that perpendicular line? I'm going to draw that perpendicular line exactly in the middle of the chord. Now, if I draw a perpendicular line exactly in the middle of the chord, then that's exactly in the middle of the circle. So not a formal proof, but just the symmetry there, right? If I'm perpendicular to that line, I can slide anywhere, except I choose to be perpendicular to the line dead center, then I'm dead center of the circle, and symmetrically I have half a circle on each side, so it's a diameter. That's kind of the logic there. But perpendicular bisector of a chord must pass through the center, or is the diameter. Okay, the second one says, if you know it's a diameter, and it's either perpendicular or it bisects a chord, then it is the perpendicular bisector. So if you have one or the other, perpendicular or bisecting, and it passes through the center, it must be both perpendicular bisector. And let's kind of look at why. So let's say we just had a diameter here that is perpendicular. Okay? So we have this diameter passing through here, and we know it is perpendicular to a chord. Okay, well, let's just draw in some radiuses. Again, these are congruent to each other. These two triangles share this side. So by HL, those two triangles are congruent to one another. And so if they're congruent to one another, then by CPCTC, all their parts are congruent. So this must be the same as this. So in other words, if it's a diameter and it's perpendicular, then we must know that it bisects the thing. That must be true. Okay? Let's do it the opposite way. Let's say instead we have a diameter that bisects a chord. So we start with a diameter. Okay? And this diameter here is bisecting. Now again, we could bisect a line segment. Like we could cut it in half in any direction. So we're trying to say because it goes through the center of the circle, it must be perpendicular. Well, let's see if that works out. Okay, I'm going to draw in my radiuses. Okay, I want to show that that's perpendicular. Well, these two triangles share this middle side, and I know the radiuses are congruent to one another. Oh, and look, so by SSS, these two triangles must be the same, so all their parts must be the same. So this angle must match this angle. And if those two angles are the same and they add up to 180, well, then they must be 90 degrees. So in other words, if it's a diameter and it splits it in half, then for sure it has to be the perpendicular bisector. It has to be 90 degrees. Okay? All right, so let's look at property number 3 here. Okay, so property number 3, again, just to recap, the first property is two congruent chords means two congruent arcs, or the same arcs mean the same chords. Okay. This one is basically saying the diameter is the perpendicular bisector of a chord, right? If it bisects, it must be perpendicular. If it's perpendicular, it must bisect. Property number 3 says, in the same circle, again, or congruent circles, two chords are congruent if and only if they're equally distant from the center. Okay, and that's going back to our original thing. That's saying that, again, right here, the distance from the center is what sets the size of the chord. So exactly that's what we're saying. If two things are the same distance from the center, two chords, then those two chords must be exactly the same length. They must be congruent to one another. Okay, so let's go down here, whoops, a little further. Okay, so in the same circle, two chords are congruent if and only if, so either direction, they're equally distant from the center. Okay, so let's prove that really quick. Okay, so on the right here we say, okay, let's assume we have two chords that are equally distant from the center. Okay, so if we draw this in, again, we know all these radiuses are the same. It's so useful. Well, look, we already have 90-degree angles. So all 4 of these triangles are congruent by HL, by hypotenuse leg, right? Because we have the hypotenuse and a leg that match in all of these. So if all of these are congruent, then what that means is their corresponding parts must be congruent. So all of these are the same. So of course, then we add up 2 of the same thing. We get the same as over here. So those 2 chords must be true, or must be congruent. Okay, back over here, let's assume instead we have 2 congruent chords. So they're equal length. Well, first thing, we're going to use our last property and say, well, we know if we have a radius or diameter that's perpendicular to a chord, it must split it in half, okay? So half of the same thing over here must match half of the same congruent chord over here. So we have these 4 pieces are the same. Okay, now that I have that, I'm going to draw in my triangles here. And I know all my radiuses are the same. And so, again, by HL, we have right angles, we have hypotenuse, we have a leg. By HL, we have all 4 of these triangles match. And so if all 4 of these triangles match, then by CPCTC, we must have this distance from the center is the same as this distance from the center. 2, 3, 4. Okay, so in other words, if the chords are equal, they're equal distance from the center. If they're equal distance from the center, the chords are equal. And again, just to highlight, hopefully this is something that's clear. When we talk about distance from a point to a line, that must be a perpendicular direction. You can't say the distance from a point to a line is some random direction towards the line. It has to be perpendicular straight at it, the shortest distance. Okay, so those are our three properties. Let's just practice some problems, okay? So we practiced that one already. Let's look at this one. We want to find the value of x when 3x plus 2 refers to this length. Okay, we got to use two separate properties here. One property is these two chords, AD and BC, are both a distance of 6 away from the center. So that means that this whole length up here must be 22. And so if that whole length is 22, we still don't know what to do with the 3x plus 2. Shoot. But oh yeah, I remember in a circle, if I have a radius or diameter that is perpendicular to a chord, it must be the perpendicular bisector and split it in half. So that means I split this 22 into an 11 on this side and 11 on this side. So that means 3x plus 2 must be equal to 11. And then we can quickly solve with some algebra. So 3x is 9 and x is 3. And it wanted us to find the value of x. Now again, the explanation was the two chords must be congruent because they're equally distant from the center. They're both 6 away from the center. And then secondary, we could split this chord in half because we have a radius perpendicular to that. So it splits the 21 into an 11 and 11. Okay, let's do a couple more. So this one, what can we conclude about the diagram? Well, in 12, it says we have a perpendicular bisector of a chord. Well, if I'm cutting this circle perfectly in half here with this perpendicular bisector, that must be the diameter of the circle. So AB is a diameter of the circle. That was one of our properties. Okay, 13 over here says, oh look, we've got a diameter and it's perpendicular to a chord, so that must be the perpendicular bisector of the chord. That again was our second property from above. So if a diameter or radius is perpendicular to a chord, it must split it in half. And then 14, well, we have a perpendicular line to a chord is congruent to a perpendicular line to a chord. That means we have two chords, NP and LN, that are equally distant from the center, and two chords that are the same distance from the center must be the same size. So we know that NP is congruent to LN. Perfect. Okay. So that kind of wraps up. I'm just going to practice some problems on IXL really quick. If you feel like you get it, go ahead and move on. And I hope you enjoy the video. All right, so here we go. This question asks, what is the measure of BE? So what is the measure of this? Well, we know CD, the chord, is 2, which is the same as chord BE, which means their arcs must match. So CD must match BE, the two arcs. So this is 73 degrees. Okay, what is, oops, sorry, let's bring this down here. What is the length of FG? Okay, well, we know these two arcs are the same, so that means these two chords must be the same. Also, FG must be 24. Okay, so what is the length of FI? Same as the last one. If the arcs are congruent, then the chords must be congruent. So this is 2. Okay, again, if the chords are the same, then the arcs must be the same. Okay, this one, oh, these are getting to be repetitive. Well, let's do a few more. So if the chords are the same, then the arcs must be the same because PQ and SR, the line segments, were the same. Sorry, it's just 57. I wrote the degrees. Okay, so let's look at this. What is the length of XY? Of line segment XY. For a second, I thought I was asking about the length of an arc. That's very different. So we know these two are congruent, and so again, this must be the same, must be 14. Okay, so now it's giving us two separate circles, but we do know that the circles are congruent, which means they're the same size. So if we have two congruent arcs, then what is, oh, and it even tells us this is 272, so we got to find the minor arc, VW. So we know that this arc up here is the same as this arc over here. So we just go 360 minus 272. So that's going to be 90, so 88, I believe. Wait, let's do that again. 60, that's one of my, so yeah, 88 degrees, okay. Let's see, so we have the two circles are congruent. What is the length of XY? So this is 307. Let's look up here. 360 minus 307 leaves 53 degrees left over, which is the same as the 53 degrees over there in a congruent circle. So XY must be the same, 50 degrees. Or if not 50 degrees, 50 as the length. Okay, so we have a central angle of 70, which means this is 70 here. Oops. Central angle 70 means this is 70 here. We're looking for the length of line segment WX. Well, these are congruent, so it must be 4. All right, well, I hope those helped out. Those were pretty simple, straightforward. But that's it. Hope you enjoyed the video.